Again, for the sake of the recording, I put those in there to complete it. Also, I want to include here something else, which is these four elements that I've put in here, HONC, there we go, HONC, hydrogen, oxygen, nitrogen, carbon. This is a nice mnemonic to remember them. HONC, obviously, but with a C, but not a K. These are sort of the main elements. They make up about 95% of what's in our body, those four elements. Most of it is actually hydrogen and oxygen. Why? Yeah, water molecules. And of those two, oxygen is by far the more significant part of what's in the body just because of atomic size. The hydrogen atom is very small compared to the oxygen atom. So even though there are two hydrogens for every oxygen in water, there's a lot more oxygen in your body than hydrogen. Also, the oxygen molecule in the air we breathe, and it's incorporated into other things. But those four kind of go with that. All right, so let me start this back up. This will take a second to initialize. You may have to log in through the clicker again as soon as this gets back up to where it's supposed to be, which is taking a long time. So we'll get there. Right now, it's not telling you anything, but so what does it say on the screen now? Okay, so if you could put your ID number again. Sorry, I wasn't thinking about the logistics of all of this exactly. But, how do I get to? Oh. There we go. Okay, so this is where we were before. So I just showed you the list of the particular combinations in HONC that are polar, and this is where we start talking about it. Yeah.
That's my user ID.
Oh, sorry. And Courtney, you're going to need yours again? Do you need your user? Okay. That's fine. 2, 3, 2. In the picture we saw a little bit ago of the hydrogen-hydrogen bond, which was nonpolar, that was where I introduced the idea of the electron cloud, that gray area surrounding the atoms. This is where, in the presentation, they first actually used that term, electron cloud. It's just kind of strange in the presentation that they started by introducing the shells, the orbital shells, and now they're talking about clouds without really explaining the difference, but it's kind of the same idea. And here's where that electronegativity really comes into effect. When the pair of electrons are shared, the one with the higher electronegativity value will attract that electron more to it than the other one in the pair, and therefore it'll have a partial negative charge. So this kind of gets at what you're saying, Aaron, about defining things as polar. The word polar refers to something that has two extremes, kind of like a magnet has a north pole and a south pole. Here we're talking across the bond, there's a positive end and a negative end. They are partial charges. It's not like the positive sodium ion and the negative chloride ion, but rather across that bond there's a partial charge. And, sorry, the picture that depicts that is coming up a little bit later on. Now, before we get to that next slide, I'd never really thought about this, but in fact it is true. Hydrogen and chloride, or chlorine, forming hydrochloric acid, is a polar covalent bond. The nature of it is actually kind of unusual. I wouldn't have picked that as the best example for this. I would have probably talked about water. Because HCl is an acid, and acids, by definition, can donate protons, and the H in anything that's an acid is a proton. So that proton comes off, and a proton is also a hydrogen ion. So the nature of HCl as a polar covalent bond is a little bit murky, because being an acid, the hydrogen ion will come off, and what's left over is the chloride ion, which makes it seem much more like an ionic bond. So this is not the best example in the world, but the electronegativity difference between them is such that it should be classified as a polar covalent bond. So the term dipole moment might seem kind of strange, but this is just describing the relationship between the two atoms in the bond. There's two poles, therefore dipole. And using the term moment refers to it as having some particular characteristics. It's a vector, has direction and magnitude. So there's going to be a positive end and a negative end. It's going to be between the center of these two atoms. So this is, again, a representation of this kind of bond, kind of like that hydrogen-hydrogen bond. We now have what represents the electron cloud here. They've colored the electrons here to suggest where they've come from. So the 7 that are red are the valence shell electrons of the chlorine atom, and the one that's blue is the valence shell electron of the hydrogen atom. And when they come together, these two atoms are going to be more attracted to the chlorine side, than the hydrogen side. Now, in the paragraph that I had you rewrite, it actually addressed why that happens. What are the two factors that determine electronegativity, according to the paragraph that you rewrote, which might have been a couple of weeks ago now?
Isn't that actually due
The syllabus quiz. I thought that was yeah, the syllabus quiz. You rewrote a paragraph that was about an electronegativity. So what were the two factors that that paragraph described that contribute to electronegativity? Distance of...
I can't remember. All I remember is distance.
Yeah, distance is going to be important. The distance from something has to do with what the other thing is. What was the other thing?
Displacement.
That would be another way of saying distance. So we're talking about partial charges. What are the charged things in an atom? What things in an atom are charged. Electrons and protons. That's basically what it is. Okay? So the two factors are how many protons there are in the nucleus. Okay? And there are 17 protons in the chlorine nucleus. There's 1 in the hydrogen nucleus. And then also the distance of the electrons from the nucleus. Okay? So there are 3 shells of electrons between the nucleus that has all those protons and the hydrogen atoms, electrons, were being shared. So that offsets the electronegativity a little bit. But if we're going to compare the bonding between hydrogen and chloride and hydrogen and something further down in the table below chlorine, then there'd be a difference here. But for the sake of comparing these two, we have 17 protons versus 1 proton, and not a whole lot of distance on either side. A little bit more distance on the chlorine atom side than on the hydrogen atom side, but still the overwhelming positive charge here is going to attract those electrons. And since the electrons are attracted to this side, it gives the chloride side the positive negative charge. I mean, that didn't come out right. The partial negative charge, which is what this figure that looks kind of like a curly QD, that's a lowercase delta from the Greek alphabet. Delta negative means partial negative charge. And on the other side, delta positive means partial positive charge. Neither side has a complete charge, like the value of an entire electron or an entire proton. It's just a little bit more negative on one side than the other. These electrons will spend time on the chlorine side and on the hydrogen side. They'll kind of, the way that this model's suggesting, they'll kind of have a figure 8 orbit. But they'll spend more of their time with the chlorine side, and that'll make that side a little bit more negative, like the chloride ion. Not as negative as the chloride ion, but kind of like it. Like I said, the hydrochloric acid molecule is a bad example for this because, in fact, if we dissolve this in water, it will dissociate into the hydrogen ion and the chloride ion, which makes it act more like an ionic compound than a polar covalent. But technically, it is polar covalent based on the electronegativities involved. Okay. Waiting for one more answer.
Yep, that's me.
Okay. So at the bottom of the screen, does it give you a check or an X? Okay, I couldn't remember if I set it up that way. I might have misled you on this question. I forgot about this question. So here's the spread of answers. Okay. As I would expect for what I told you, there's a lot more people that chose C as an answer. Because I told you that nitrogen-oxygen bonds are polar. But what was correct? Oh, good. I was afraid that it was going to tell you that A was actually correct. I couldn't remember. So we already dealt with sodium chloride. That's an ionic bond. Okay. Sodium fluoride is going to be an ionic bond too. Okay. Chloride and fluoride, or chlorine and fluorine, are right next to each other on the table. So I was afraid that this was going to say, because lithium and oxygen aren't quite as far apart, they don't have quite as big difference in electronegativities. I was afraid that was going to be the correct answer. But no, in fact, it is no. Good. I didn't mislead you. What I told you is entirely correct. Now, what I put on the screen at the beginning, or beginning of the second half here, that second list of polar things, this would be when I would actually give you that list, but I can't switch out of the presentation to do that. So that's fine. Okay. Oh, sorry?
My stomach keeps like.
Yeah, we got to be talking about sugars and stuff. So, and then, whereas right after that last question is when I would have given you the list of the polar bonds, this is where it actually introduced that HONC thing. Because those four elements make up more than 95% of our body. Glucose or fructose both have chemical compounds of C6H12O6. The particular arrangement of those 24 atoms is different between the two, but they have the same 24 atoms in it. And obviously they're made up of those. Neither of them have nitrogen in them, but that doesn't mean that nitrogen's not important. Nitrogen is found in other things like proteins and that sort of thing. Sorry? So the other 4% there represents all the other elements that are in our body. They fall into kind of two categories, and I don't really make a big distinction about them. There are trace elements, which are found in very low quantities, usually less than a fraction of a percent. And then some sources will call them lesser elements or something like that. There are a few things like phosphorus and sulfur and sodium and chloride, and I can't think of all the other ones again listed there, but there are certain things that are usually in the 1% or higher range, but they don't get into the top notch.
Calcium is like necessary in neurons.
Right, and we have a lot of it in our bodies because it makes up the crystal structure of bones.
Yeah.
So this is a natural bone, and what we're looking at here is the crystal salt structure. It's a calcium crystal structure. So in this, there's a lot of calcium right there in your bones too. So yeah, there's a lot of it there, but it doesn't make up enough to fall into that upper group with the other four. But it's more than a trace element. So we've already addressed this, that earlier question that had as an answer C2H2. There are polar non-polar covalent bonds there. But anytime carbon and hydrogen make a bond, they're non-polar. Nick's response here is kind of partial we've already covered, which is there. Wait a second. Oh. So let me get off this slide. We'll talk about that in a second. But I do want to address this carbon-hydrogen thing. Any molecule that has carbon in it is by definition organic. But being organic doesn't necessarily mean that it's good for you. Methane is toxic. Now, you have methane in your body. It's a waste molecule that certain little bacteria living in the digestive system give off. And it's contained within that digestive system, and you release it every so often, to the complaints of those people around you, I'm sure. But you would not want to breathe in methane in any large quantities. It would be essentially poisonous. Just as an aside, if you're buying food because it's labeled as organic, that's really a marketing ploy. Sure, there are certain things that define things as being organic, but there's probably not anything terribly important based on what's organic in the supermarket. If you really want to get, produce or something like that that's organic, you need to know the farmer. You need to know what they do to do that. Oftentimes, organic produce will claim to be pesticide-free or something like that. But there are pesticides out there that are naturally occurring in plants. Nicotine is a pesticide. We happen to use it as a drug, but it actually will kill various types of invertebrates that want to eat tobacco plants. So be careful about terms you hear. Organic officially just means anything that contains carbon in it. Okay? And there are organic molecules which are detrimental to our health. So, but going on there, this goes on to talk about hydrogen bonding, which is the last aspect of what this little story is doing. Now, I've never had a real comfortable, straightforward definition of a hydrogen bond. So this is fine. It can seem a little confusing, so I want to parse it out a little bit for you. When hydrogen is part of a polar covalent bond, meaning when it's bonded to oxygen or nitrogen, but not when it's bonded to carbon or itself, it can be attracted to other elements within a molecule. This is not the same kind of bonding as what we've talked about. This isn't atoms coming together to make compounds. Rather, this is when two compounds or two molecules are attracted to each other. And so if there's hydrogen bound to oxygen or nitrogen, therefore an apolar bond somewhere in a molecule, that hydrogen has a partial positive charge, and it'll be attracted to a negative charge, whether that's a partial negative charge or a full negative charge. So a little bit more on your question earlier, Aaron, about ionic and polar. Polar can often be used to describe things that participate in hydrogen bonds. And you can have a hydrogen bond where the hydrogen is attracted to a chloride ion or something like that. So by that definition, then yes, ionic compounds are polar. But in the sense of a polar covalent bond, they're not, because they're a different type of bond. But they behave in similar ways. Now, Nick claims that it's making sense to him now, but I don't think from that definition that it's necessarily that clear. Here we have sort of the primary example of a hydrogen bond. So hydrogen, when it bonds to oxygen, is polar. There's going to be a partial positive charge on the hydrogen side and a partial negative charge on the oxygen side of that bond. Okay. And then there's another one over here, so we have a partial positive, partial negative distribution across this bond too. And then the same thing in this other water molecule. When the partial positive charge of the hydrogen in the water is close enough to the partial negative charge of an oxygen in another water molecule, they're attracted to each other. It's a very weak attraction. Now, I have these models, again, the idea of understanding something, but these are little 3D models of water molecules. They have in them strong little magnets, so they can stick together like that. Okay. Now notice that the white, which represents a hydrogen atom in the water molecule here, is sticking to the red, which represents the oxygen atom in the water If I try to put two hydrogens together, they actually repel each other. And you might not see it exactly, but I can definitely feel the repulsion when you're trying to push two magnets together that are oriented, south pole to south pole or north pole to north pole. Okay. So they repel each other there, but they attract each other there, representing the attraction between the partial positive and partial negative charge. The thing is that with water, the molecules are always in motion. Now, the amount of movement within a water solution, or really in any substance, is directly related to its temperature. So the hotter something is, the more it's going to move. So as I'm taking these water molecules and sort of jumbling them up in my fingers, between my fingers, you can hear the clicking of the little water molecules coming together where the magnets are attracted. Okay. But they're also continuously being broken as I'm moving these water molecules back and forth. That's what I mean by a weak attraction. Okay. They can be broken pretty easily. It's just a matter of temperature. For water, if we heat water up, eventually it'll break those hydrogen bonds so much that the water molecules will never be attracted to each other. What do we call water when it's in that state?
Gas.
Yeah, it's a gaseous state. We call it water vapor or steam. Water vapor isn't necessarily at the, above the boiling temperature, but steam by definition is. If you were to take water molecules and physically pull them apart, which we can't, grab two water molecules with tweezers and physically do that, but if the concentration of water is low enough, they'll physically be separated by each other even at below boiling temperatures. In fact, outside right now, it's definitely not anywhere near boiling temperature. But in all of the snow out there, there's a process called sublimation where water molecules are sort of slipping out of the snow and vaporizing into the air around them. Temperature isn't necessary, but it's pretty easy to describe how that can change, just in boiling temperatures, boiling water. Now, I have here demonstrating this 12 water molecules, okay? They're little models I use. But the reason I have 12 here is because actually I have a bunch of these in my office, and I grabbed a bunch, because here's 12 more water molecules that are now in a different configuration. As the temperature drops in water, the hydrogen bonds become more stable. They're still kind of weak. You can break them like I just described out there. There's sublimation, water molecules coming off of the snow out there. But they stabilize into a crystal structure, which is represented here. And this is what we call an ice crystal. Now, you should be able to see from wherever you are in the room that there is actually some space in between the water molecules here. Just as all of the hydrogens and oxygens come together in that crystal structure, come on, they're going to be further apart from each other than the 12 molecules that I have in my other hand. Okay, so this is an ice crystal. This would represent a very, very, very small drop of water. The close packed nature of these molecules here in the drop of water version that I have is denser than the crystallized structure here. Okay. Water is actually more dense as a liquid than it is as a solid. For most substances, the opposite is true. We usually think of solids as being more dense than liquids. But you have personal experience proving that liquid water is more dense than solid water. What is that? Yeah, ice water. Ice always floats at the top. It's therefore less dense. If it was more dense, it would sink. Right? Just like if you took, gold and dropped it into the water, it would sink to the bottom. Took gold and dropped it into molten gold, it would sink to the bottom, okay? Because of a density issue. But with water, it's actually most dense in its liquid form. And actually, it's most dense precisely at 4 degrees Celsius. That's sort of the trade-off between enough temperature, enough heat to break those hydrogen bonds regularly, but not to move the molecules away from each other so much that they start to expand eventually to become a gas. What do you have at home that is 4 degrees Celsius?
Like milk, right?
Well, where do you keep the milk?
Refrigerator.
Yeah, fridge. Okay. Now, I asked that in Celsius because this is a science class and we want to think about metric units. But you're probably more used to Fahrenheit, and that temperature in Fahrenheit, 4 degrees Celsius, is about 40 degrees Fahrenheit. Okay. So the temperature in your refrigerator is about 40 degrees Fahrenheit. And that's useful for preserving foods because at that temperature, it inhibits bacterial growth as much as possible without damaging the cellular structure of the food that's in there. Okay. Now you can freeze a lot of stuff and it'll preserve longer, but that can sometimes cause problems. What happens if you freeze strawberries and then you thaw them out to use them? Yeah, they get all mushy. It's because the ice crystals will end up breaking up the cellular structure of the strawberries, which ruins the strawberries if you're trying to make, something with pretty strawberry structures. But if you're making smoothies, it's great. Freeze the strawberries, put them in the blender, chop them up, and it'll be a great smoothie. But that's because cellular structure doesn't matter. But that 4 degrees Celsius is sort of the ideal temperature where water's at its most dense and it actually inhibits bacterial growth as best it can without freezing it. So those are hydrogen bonds. Okay, one more person. Here we go. Okay. So here's the distribution of answers. Few, at least one for everything, a couple for C, but most for B. Which one's correct? Oops. So now, from the definition that was just given a couple of slides back, they use the term electronegativity quite a bit. And so that's in the definition here. Also, this is not bonding like the other thing. We're not talking about sharing or transferring electrons anymore. Rather, just the attraction between two things.
But electronegative a hydrogen atom attached to an electronegative atom is not attracted to the electronegative properties of the atom.
Yeah, you're spot on, and I was about to say this. I don't really like this definition. And like I said earlier, when there was the definition in the slide, it's not a great one. But here they really kind of ruin it. The point they're trying to make here is when hydrogen is attached or bonded in a polar covalent bond, meaning to another atom that has a stronger electronegativity than hydrogen, it can then be participate in a hydrogen bond and be attracted to another atom that is also in a polar covalent bond, but that's going to be the one with the partial negative charge. If I were to try to make sense of this particular definition, the best I could say is a hydrogen atom attached to, or a hydrogen atom within a polar covalent bond in one molecule is attracted to a strongly electronegative atom in an adjacent molecule. All atoms have some electronegativity. Some are weakly electronegative, some are strongly electronegative.
And so C, not necessarily, it's always true, but it can be true. And right?
Well, if we're talking about what the hydrogen bond is, C is not correct, because that's the definition of a covalent bond. The hydrogen is going to be in a covalent bond when it's attracted to something else. That's certainly true. But yeah, the definition in B is not the best. But to say a strongly electronegative atom would be something like oxygen or nitrogen, which are strongly electronegative compared to the other elements that we're concerned with. So it's not an ideal definition, but for what's written up here, it's the best choice. So basically, yay, this is all great. Here they're trying to talk about the importance of hydrogen bonding, and you can read it if you want to, but I don't think this is very crucial, which has to do with how DNA plays a part. But I'd rather stress something else, which comes back to this model I have of protein structure. A protein is a strand of amino acids all covalently bonded to each other, but then they will be attracted to other amino acids within that structure through hydrogen bonds most often. So to make a helix shape like I have here, if we were to pull this apart, the first amino acid in the chain is attracted to, say, the fourth amino acid. And then the second amino acid is attracted to the fifth. And then the third is attracted to the sixth. Fourth is then also attracted. And so it just starts making this corkscrew shape because there's these hydrogen bonds forming in a regular pattern. 1 to 4, 2 to 5, 3 to 6, 4 to 7, 5 to 8, et cetera, et cetera. And that will start to make this kind of bonding pattern. With this flat sheet here, what we're seeing is attractions between, say, 1 and 7, 2 and 6, 3 and 5, 4 is at the corner, et cetera, et cetera. And so they sort of fold back and forth like that. That gives the protein some shape. Now, earlier we were talking about the fact that maybe ions are important for different major parts of proteins to be attracted to each other, but a lot of times the structures within proteins are largely defined by hydrogen bonds. In here, they're talking about DNA and zipping and unzipping and that sort of thing, which is fine. It's a great idea. We don't really concentrate on DNA too much in this course. Proteins are by far more important to understanding physiology. But if we were to take apart a protein, if we were to allow all of those hydrogen bonds to separate, then the protein would lose its shape like this. Okay? Now, who had eggs for breakfast this morning? Nobody else? Come on, people eat eggs. They're good for you. Okay, so you kind of ruined that whole setup, but let's pretend you did eat eggs. I ate eggs for breakfast this morning. In cooking eggs, you are doing this to proteins in the egg whites. Okay? So what do egg whites actually look like in an uncooked egg?
Clear.
One, they're clear, and two, they're kind of gloopy. Okay? They're very liquid. What do they look like after you cook it?
Solid.
So they're solid, kind of a rubbery texture, and they've now become an opaque white color. What's happening there is a protein in the egg called albumin, technically albumin, gets denatured by the temperature of the pan that you're frying your egg in or whatever. And the protein kind of unravels. All of those hydrogen bonds are broken. The covalent bonds aren't broken. Heat will not break a covalent bond. But then other things are changing and the protein might take on a different shape. I always make these kind of pretzel shapes, whatever, but a bunch of albumin molecules that were denatured by the heat will then sort of reform and make this mesh of kind of rubbery opaqueness, which is the cooked egg white part. Okay. There's an article that I just read recently about unboiling an egg or uncooking an egg. So we'll stick with the boiling an egg idea. You take an egg, you put it in boiling water, you leave it there for long enough, and when you take it out, you've got a hard-boiled egg in the middle. There are things you can do to reverse that process. Now, yes, it does sound kind of strange because truthfully, the only reason anybody would want to do that would be because they're weird. No. Because they're these kind of chefs that like playing with chemistry in the kitchen. To unboil an egg, a chef that does this actually it takes at least as long as the boiling process, if not longer, and you have to treat it with chemicals which will, again, denature the proteins, but then at lower temperature, they'll form back into their original shape, and you have unboiled eggs. Okay. Why anybody would want to do that, I have no idea. It sounds kind of disgusting. But maybe you boil the eggs, you get rid of any salmonella bacteria or whatever in there, and then you unboil it, and then you can eat a raw egg without worrying about eggs. I don't know. There are people out there that will eat some really weird things.
Yeah.
But the article that was talking about this was talking about unboiling an egg, but not for the purposes of any kind of cooking procedure. Rather, they were just trying to prove that they could do this because they came up with a way to do it in minutes instead of, well, like 3 minutes instead of 15 or 20 or however long it took, or hours it took before. And they didn't care about actually making an egg that you could eat in that form. They were really trying to figure out ways to change protein folding quickly. So earlier there was a slide that was talking about folded proteins and referred to Alzheimer's disease and human variant mad cow disease, those sorts of things, which are the result of misfolded proteins. So what if, because somebody figured out how to quickly unboil an egg, they also knew how to quickly change the misfolded proteins in somebody with Alzheimer's back to the way it's supposed to be, and therefore reverse Alzheimer's. That's probably where the research is headed. But essentially it was by manipulating the changes that happen when you denature proteins and kind of like that. So this just ends like, yeah, great, you learn a lot of stuff. Let's just go through some other questions. So there are a few more questions here. They're just going to come in a row, kind of reviewing some of the things that have come up so far in the presentation. One more. Check your screen. Make sure you submitted your answer. There we go. So there are the answer responses. Which one's correct?
C.
C, yeah. When you have two of the same thing binding to each other, that's by definition going to be nonpolar. Also on the screen here, the lithium fluoride is an ionic bond. Okay. The other three are covalent. Again, HCl is kind of questionable, but technically it is. But water is definitely a polar covalent, but a fluoride to fluorine to fluorine bond would be nonpolar. Has it not said ABCD yet on your screen?
No, not yet.
Whoops. Does it say it now?
No.
Okay. One more. Thank you. Yay. Okay. One person whose thumb slipped, but other than that, what's the obvious Q word here that should point out that D is the correct answer? Yeah, remember the definitions kept dealing with electronegative. Not a great definition, but that's where it's going with that. You got the answer choices for this one?
Yeah.
Okay, good. Okay. Which one's correct? Again, electronegative, and D is a clue that's talking about hydrogen bonds. What is C referring to? Polar, right. And what's B referring to? Nonpolar, covalent. So B and C are both talking about shared electrons, so those are covalent, and equally shared would be nonpolar, unequally shared would be polar. Okay. One more person. Make sure you submitted your answer. Great. Okay. So a little bit of range. Which one's correct? D. Okay. So when we see a line between two representations of atoms like this, that usually suggests we're talking about a covalent bond. But also hydrogen-nitrogen bonds were on our list of the polar bonds, which being polar means that it's covalent too. There. It's not coming up, is it? Nope. Anything yet?
Oh, it is.
There we go.
Oh, shoot.
Okay. So there's our range of responses. Now, in this question, actually, there's only one possible correct answer. Because valence electrons are found in a single shell. And only one of these numbers represents a number of electrons that could be found in a single shell, which is what?
The third one outside.
C6. Now the numbers they're dealing with here, 16 would be the total number that we see here. 10 would be the inner two shells, 8 and 2. And then 14 would be the outer two shells, 6 and 8. But valence is the outermost shell. And also no shell can hold, of the electrons that elements that we're talking about, no shell is going to hold more than 8 electrons. So all of the choices here are too high except for C, just based on that idea there. So yay, we're done. Actually, there's this one more thing. This is not something that you can do with the clickers, but you could complete this table from the material that's been covered in this with the different types of bonds. There's a bit of information in each row or each column, so you can figure out what's supposed to go where. But if you'd like to try to complete this. Now, I don't want you to sit here and copy this down right now because that would take a long time. If you would like to look at any of this material in more depth, if you were trying to write down some of the stuff on the screen earlier or something like that, and you didn't get to all of it, you can go to the recording and all of those slides are available right there. And I will put the link to that YouTube channel for you later on. One last thing I want to deal with here, we already talked about polar and nonpolar, a little bit more about honk. And I'm going to put it in this order here. Besides just reminding you of the 4 most prevalent elements in your body, honk tells you something else, which is how many bonds each of these elements can participate in. So when an atom is participating in a bond, it's trying to fill its valence shell. Okay? And here I'm talking about covalent bonds. When hydrogen participates in a bond, how many electrons does it need to fill its valence shell? 1, okay? Because it belongs to that first row on the table, hydrogen and helium. Those 2 elements are in that row by themselves because that first shell can only hold 2 electrons. Hydrogen has 1 already. It can pick up 1 more. Okay, so hydrogen can make 1 bond. Okay. Now, oxygen has 8 protons, which means that it's going to have 8 electrons. How many of those electrons are going to be in the first innermost shell? 2, because that's all that's ever there. So how many are going to be in the second shell?
6.
6. 8 minus 2 is 6. So how many electrons does it need to fill that outer shell when it's making bonds?
2.
2. So how many bonds can oxygen make? 2. Okay. Oxygen, like I just said, is has a atomic number of 8 or 8 protons. Nitrogen is right next to it in the table. Okay, it's a little bit further to the left side, so it's one less. It's an atomic number of 7. It has 7 protons. So how many electrons are in its valence shell?
5.
5. 2 in the center, 2 from 7, 5 more, and the next one. How many does it need to fill that shell?
3.
3. So it can make how many bonds? It can make 3 bonds. And then carbon is right next to nitrogen on the table. So oxygen was 8, nitrogen 7, carbon is 6. How many bonds can carbon make? There's 2 ways to get there. One is to just do the same kind of math, that 6 protons means 6 electrons. There's 2 in the inner, then that means there's 4 in the outer. You need 4 more to complete that shell. Or you can just look at this and notice that we've got a little pattern. So honk also reminds you in order how many bonds each of these can make. Why this is important is because when we're talking about different molecules, sometimes that's going to be relevant. Right? For organic molecules, they're based on carbon. So carbon makes 4 bonds. You can have a chain of carbons and then things sticking off of that chain because of all the bonds that they can make. So this is a useful another little mnemonic to put in there. Now, I just wanted to touch on some things in the chemistry stuff, concentrating on the bonding aspects. Let's see. Oh, whoops. Oh, that's right. I moved to the AMP2 to show where that link was. Let me go back to your class, year 5. Okay, so we're currently in the chemical organization chapter. There is certainly more to this chapter that I want to just highlight real quickly. Just looking at the contents of the chapter, not that you can necessarily read it from where you are, but this is the introduction. Then it starts to talk about elements and atoms and the building blocks of matter, which is that, and the next section, which is chemical bonds, is largely what we've been talking about here. Some things about chemical reactions, which is useful to kind of understand basically how things will interact. We don't get into too many reactions themselves in this course, but it's useful for you to have that kind of background. And then it has inorganic and organic compounds that are essential to human functioning, both of which you need to look through. But I want to point out some organic compounds that are important, which are what we refer to as the macromolecules. So first it just talks a little bit about the chemistry of carbon, which is important. Then it introduces this thing called functional groups. So pay attention to this. I'll mention some of these things occasionally. Then it goes through what we call the major macromolecules. There's carbohydrates, which are often referred to as sugars, showing a few different types there. And then lipids, which are often referred to as fats. And phospholipids being some of the more important types of those, especially for this class. Proteins, explaining the structure of how they bond together, how amino acids make up a strand that we call a protein. And then it gets into talking about shape. It's a little unfortunate in the book here, they don't go into this in a whole lot of detail. This figure kind of sums up all the really important stuff that you need to get. Here we have a strand of amino acids. Here, that strand of amino acids represented by this ribbon is forming a particular structure, which it's kind of hard to tell in 2 dimensions, but this is that helix shape I just showed you. And the dotted lines represent the hydrogen bonds. So amino acid 1 is attracted to amino acid 5. I used the wrong numbers. 2 to 6, 3 to 7, 4 to 8, 5 to 8, nope, 5 to 9, 6 to 10, et cetera, et cetera. And because of that pattern of attractions, hydrogen bonding reactions, we get that basic structure. And here we see a sheet. Okay. Amino acid 1 attracts amino acid 7, 2 to 6, 3 to 5, 4 is in the corner, and then 7 to 9, 8's in the corner, 6 to 10, 5 to 11, sets up this kind of flat sheet shape. These things, the helices and the sheets and other things that books never bother talking about, are considered the secondary structure of proteins. And then as we start to look at all of those structures together within a single protein strand, that's the tertiary structure. If we have multiple protein strands coming together forming a larger superstructure, that's the quaternary or fourth level structure. In this picture, and a lot of examples like this, they'll use hemoglobin as the example because hemoglobin is made up of 4 separate subunits. This would be one subunit here. So 4 of those sorts of things all come together to make hemoglobin. It's summarized in the figure caption down below a little bit, and the book addresses a little bit. I really wish the book would address it a lot more because it's terribly important. The primary structure, the strand at the top, those are covalent bonds. Everything else is essentially based on hydrogen bonds. And hydrogen bonds can be broken pretty easily, like I said, with boiling an egg. You're breaking those sorts of things. You're denaturing the proteins, and it changes how they fold. Okay. So I want to be sure that you're aware of that. If you don't feel that the book is really explaining it fully, please find another source and get some more information about it. But it is important stuff. Right, there's a lot of places online. So you can just look up shape of proteins, a little vague. Protein structure, protein folding, secondary structures, tertiary structures of proteins, those kinds of things. And you should be pointed to some useful sites online to get more information about it if what's covered right here doesn't really satisfy you. Talks a little bit about enzymes and other proteins. And then the 4th macromolecule are nucleotides, which polymerize into nucleic acids, like DNA and RNA. They have nucleotides separate from nucleic acids because there are some nucleotides that don't polymerize, and they're very important. Like you've probably heard of ATP. ATP is a type of nucleotide. It's not polymerized. In its own right, it's a very important molecule. But then DNA and RNA are nucleic acids. So here's where they talk about ATP down here. So be sure that you pay a lot of attention to that stuff. Protein structure is probably the most crucial part of what's in here. Now, next week, I'm actually going to talk a little bit about protein structure in some detail because it'll have something to do with what we're doing next week. But we're going to concentrate next week on the cellular component or cellular level of organization. If you go to the next week, sorry. Oh, yes, sorry. Of course, I'm used to teaching week by week, so I'm thinking, but next lecture, yes, which is Friday, we're going to be moving on to the week 3 material, which is the cellular level of organization. In talking about this, what we're going to do is actually look at a case study that talks about a disease that at its root is about what's happening with chemicals and cells in the body. Now, you have that case to read available to you in Blackboard, and I want to show you where that is. In the weekly material folder, click on that and go to the week 6 folder, which is the lab practical folder. So when we get to week 6 eventually, which is going to be, let's see, we'll be done with the week 4 material by next Wednesday. So yeah, so it looks like it's going to be the beginning of March there. I'll double check the dates before we get to that. But in this folder, you'll find a link here at the top that says Practical 1.1 Cases. If you click on this, it'll take you to this document, which contains 4 case studies, 4 descriptions of clinical situations. On Friday, in our next class, we're going to look at case 2 here, okay? So go to this document, again, from Blackboard, click on the cases link within the week 6 Lab Practical 1 folder under weekly material, and you'll go to this. You're welcome to look at case 1, 3, and 4 that are also on this, but case 2 is what you want to pay attention to. Now, when we're using case studies in this class, we're trying to get a feel for how the basic anatomy and physiology that we're studying relates to clinical cases, which might be relevant to the career that you're planning on going into from here. And in looking at these cases, I have this kind of way that I want you to approach them. First off, make sure that you understand the terminology in the case. Now, primarily definitions are important. If you don't know what the words are that you're reading, then you're going to be kind of lost. But it goes a little bit further with that in science and medicine kind of circles. Besides just the meanings of words, there are some things that are special uses in science or medicine, what we'd call jargon. So for instance, you might know what the word blood means, and you might know what the word pressure means, but blood pressure as a term has a very specific meaning in medicine. So if you're dealing with blood pressure in a case like this, be sure you understand what that's referring to, and the case will probably have some data, what the blood pressure for the patient is. Be sure you understand what that number means in reference to the normally accepted values of that. And then also be sure that you understand abbreviations. In this case that you're going to be looking at here, there's quite a lot of abbreviations in here. I want to point 2 of them out because they're really not defined within this, and they might be kind of confusing. The first thing is it starts off saying WM is a 22-year-old female with cystic fibrosis. WM are her initials. So don't try scouring the internet trying to figure out what WM is an abbreviation for. It's just her name. Okay, that's not terribly explicit in the case, but that's what's going on. The other thing, a little later on, it has CF down here, and it's going to keep saying CF over and over. That's just an abbreviation for cystic fibrosis. I really ought to put in there for you guys. I put it in. So now it defines that as the abbreviation CF. Okay. But otherwise, there are a number of abbreviations: BPM, HENT, FEV, et cetera, et cetera. Be sure you understand what those abbreviations mean. Okay. So going through that means you understand what's in front of you. You understand what's written, and you can make sense of it. Now, these are always stories. Okay. Patient walks into a doctor's office and says, "Hey, doc, it hurts when I do this." From that story, what you need to be able to do is pull out the symptoms and signs that are described. Now, I don't really care about the difference between what a symptom or a sign is. There is a particular meaning to the 2 words, but both of them are basically referring to any loss of function. Okay? So as you're reading through the case, make note of the things that don't work for this person. Okay? The first thing you're going to come across is that she has a cough. That would be a symptom. Okay? And there's a lot more to go, but I got you started there. First one's cough. Then I want you, from the list of symptoms or signs that you've come up with, those functions that have been lost, come up with a list of the systems that are related to that. Specifically, those are the organ systems that are affected. So if she's got a cough, which organ system is that a symptom of?
Immune system.
No. Respiratory system, right. She's trying to force some sort of fluid out of her lungs, so she's coughing. So that kind of thing. Just with each symptom sort of connected directly to the organ system that's affected by it. Don't try to get to the underlying cause of things. Just on the surface, what is the relationship between the loss of function and the structures that are there? Okay. And structure and function is anatomy and physiology. So in doing this, you're going to be looking at what the underlying anatomy and physiology is in the course. Okay. Next week, when you come in, I want you to have read through this case and be sure you understand all these parts of what's going on. And we're going to discuss the case. We're going to start that discussion with me asking you what terminology you weren't familiar with coming into it. And then we're going to go on with me asking you what symptoms or signs did you find in the case. And then I'm going to ask you which organ systems each of those symptoms or signs are associated with. So I expect everybody's going to walk in knowing that information, and you're going to carry that part of the conversation. I'm just going to ask you those 3 questions, and you're going to do the rest of them. Okay. And then from that, we'll understand what's at the root of this case, and from that, understand some of the basics of proteins mostly in cells and that sort of stuff, and how all of that impacts the normal functioning of the entire organism when we get to it. Okay. So for next week, be sure that you go in and read that case and make sure you can do all of this stuff with it. So, any questions about what I'm asking you to do? Yeah, Sophia?
I'm not sure about this, but the week 2 stuff in the folder.
Yeah.
We already did the learning pods, but for the quizzes and stuff, is that due by Friday or this Monday?
Yeah, so when they announced that we were going to be closed on Monday the 2nd, they didn't announce that until the morning. So as of midnight on Sunday the 1st, I had to operate on the assumption that we had school. I knew that probably wasn't going to be true, but the school sometimes does this thing that they expect a big storm, so they close for the first one, and they realize, oh, we didn't need to really close because it was like 3 inches. And then the next storm comes through, and they say, well, we got caught last time, so this time we're not going to close. And then it's like, feet and feet and feet of snow, and they should have closed down. So I was entirely prepared for the school to decide to stay open on the 2nd. And so I didn't want to say anything. So those due dates for the 1st, which included the learning pods for the biochemistry stuff, were in fact due then. As far as the rest of that material, what I've done as the snow days have progressed, I just gone into this system. This is a great way for me to keep due dates straight. So here's a 2nd, and here are all the things that were due by midnight on the 1st, which are all of the introductory chapter assignments, as well as the learning pod assignments for chemistry, and also the learning pods from the introductory chapter, which technically were due on the 25th in the system. I told you that you had that whole week, so you should have finished all of that stuff by the 1st. But of course now, here we are down here on the 17th. There's nothing due coming in today because you did everything that you should have back here. Our next class meeting is on the 20th, so yes, to keep up with things, these things are due by the 20th. There are learning pod assignments on cells, cell biology and the cell chapter learning assignments, only 2. That's not too bad. And then the biochemistry chapter assignments are in there too. Now, if you're a little pressed for time and you can't necessarily get everything done, definitely get the couple of learning pods out of the way first, because if you don't get them done by midnight on the 19th, then you're not going to get full credit for them. So definitely do those first. And then work on the chapter assignments, part 1, 2, 3, 4 assignments. If you can't finish all of those by midnight, please try your hardest to get through part 3 by midnight. Okay? If you don't finish those by midnight, then when you do finally get around to them, since they're late, you won't be able to go through them as quickly. You do part 1, I have to check off that you've completed part 1 before you can do part 2. Then you do part 2, and I have to check off that you completed part 2 before you do part 3. And then you do part 3, and I have to check that off before you can go on to part 4. If you at least get parts 1, 2, and 3 done by their actual due date, and you don't get around to part 4, you do that late, and it won't affect anything else. Okay, you can get to that. Also, there's a molecular lab quiz in there, okay, which has some stuff about protein folding. So be sure you're comfortable with that before you get into doing that lab quiz. But if you don't do the lab quiz or you don't do part 4 before the due date, that's not going to be a big problem. Only the learning pods are date dependent on getting them done. And then the part 1, 2, and 3 assignments, if you don't get them done by the due date, then it's a little bit of a nuisance later on when you're trying to complete them because you don't get to move on to the next part right away. So if you at least get the learning pods and the part 1, 2, and 3 assignments done by midnight on Thursday, and you do the other things which are due afterwards, you won't suffer grade-wise. It won't affect your score at all. And those assignments, part 4 and the lab quiz, won't, I can't remember what I was going to say there. They're not dependent on anything, so if you get them done late, they won't mess anything else up. But keep in mind that we're just going to keep barreling through here. Okay? So on the 23rd, we're going to do oh, that's weird. Okay, I got to move these 3 here, right? Oh, I see what I did. Okay. So we're going to do the cell stuff here. So then on the 23rd, we're going to do the tissue. The LPs, learning pods for tissues, are due before then. Okay. What I decided to do was to go ahead and push the due date back on the cell biology work, which is actually what we're doing on Friday. Those due dates are the 24th, just to give you a little bit of time. You will hopefully get them done over the weekend, but if you don't, you have a couple more days before the due date is set in. The tissue due date stuff is all on the 1st. Okay? We're actually going to be doing the tissue stuff on the 23rd, but I didn't make them due on the 25th because I thought that was just a little too soon. So we're going to push that back. I'm not quite sure if on the 25th we're going to be doing the skeleton and skin stuff, or if I might end up pushing that back a little bit too, just because it's all coming kind of quickly. In the system right now, the 2nd, which is at the bottom there, is the date that the practical is scheduled for. But I really want to see how we get through these 2 weeks. A lot of stuff coming quickly, and I might decide to push the date of the practical back a week so we have more time to deal with this stuff. And if that happens, we'll figure out what's going on. As far as the due dates are concerned, I think this is as comfortable as I can make them in here. Okay. So, any questions about due dates? Having looked at that. Again, remember, when you open up an assignment, it'll tell you when it's due, so pay attention to that. And definitely through the rest of February, all the due dates, as I have them here, is how I'm going to leave you. We might get a little bit ahead on some of the content that we cover, but I'm not going to make things due earlier than they are here, just because I think it's getting a little tight in these next couple of weeks, and I want to be sure everybody has time to complete stuff. Any other questions? All right. So if you don't have any other questions, that's it for today. Don't forget to read through that case study and be ready to discuss it next week.